Hello, my name is Sylvie Le Guyader, and I'm going to give the introduction to the speed workshop, which has been created by Tobias Nyberg and will be presented by him. So why do we want to image fast? In general, it's because we're imaging in multi-dimensions. Maybe we want to do Z-stacks, tiles, multiple wavelengths, or time-lapse, or even multi-well combining all this. Basically, it's taking a lot of time. So in this workshop, we are going to compare several modes of confocal imaging. We will have a single point confocal with two types of scanners, a galvanometric scanner, which basically is the name of the normal scanner that everybody has in their single point confocal, and then a resonance scanner, which is a faster scanner. And we will also compare with a multi-point confocal, which is a spinning disk. So therefore, we'll have a comparison of three different modes: single point confocal with galvanometric scanner, single point confocal with resonance scanner, and multi-point confocal. The things that will be common in the three modes is the sample. So this is a convallaria cross-section. It's an autofluorescent piece of plant. We will always have the same objective. It's a 20x air NA 0.75 objective. And we have done our best to keep the pixel size constant. So we have about 0.5 micron per pixel. And we have the same microscope. I will show it to you. And then the difference is that, of course, we have a single point confocal on one side. So there is only one spot of excitation and emission. However, what will make it go a little bit faster is that we have 4 detectors. And we have a resonant or galvanometric scanner, so the resonant will maybe make it go a little bit faster. And as you know, on a single point confocal, we have the flexibility to change the pixel size and adjust also the pinhole. On the multi-point confocal, we have thousands of excitation and emission spots at the same time. And we have one camera, but it has millions of pixels. However, the pixel and pinhole sizes are fixed. So this is the microscope we're going to use. Here you can see the microscope. And on the left side of this microscope, we have the single point confocal with the resonant and galvanometric scanners in the black box and the 4 detectors in the white box. And on the other side, we have a multi-point confocal where we have a spinning disk and a camera. So in this workshop, we're going to talk about the noise a lot. The shot noise is the noise that comes from the fact that light has a statistical nature. So we cannot image light without having shot noise. The shot noise is the square root of the signal, which means that if we manage to increase the signal, we are actually decreasing the proportion of shot noise. Unfortunately, when we try to go fast, this is not what we do. When we image fast, we collect less photon, and therefore we have a higher contribution of the shot noise. So in this workshop, we will try to go fast and try to compare the impact on the signal-to-noise ratio in the image. So here is a little reminder of the single point confocal principle. So we have a laser that sends the light to the scanner, and inside the scanner we have 2 mirrors, one that scans the light in the X direction, and the other one that scans in the Y direction, and together they are moving in such a way that they scan the spot of light across the whole sample through the objective and across the whole sample. So we're going to compare a galvanometric scanner, which is slow but with adjustable speed, to a resonance scanner, which is fast but we cannot change the speed. So as a reminder, in a single point confocal, what we do is that we send the excitation light to the sample, and then we move the excitation light spot to a certain distance, which is the pixel size, and then we record the emission. And therefore, depending on how much we move between spots, we're going to have different pixel sizes. So we can decide to either fill up our field of view with small pixels, lots of small pixels, or fewer larger pixels, and then we record the whole image. So the pixel size, we can choose the pixel size. Something else that we can change on the single point confocal is how long the laser is going to stay on each spot before it jumps to the next spot, and this is called the pixel dwell time. And the next thing that we could change is the field of view. So we can keep the same pixel dwell time and the same pixel size, but we could decide to scan less spots, and therefore our image will be smaller. Additionally, what we can do is that we can scan a whole line of pixels and then jump back to the beginning of the line and scan again. This is called unidirectional scanning, so we're scanning only in one direction. Or we could scan the line and then move, when we move back along the next line, we could scan again. So this is called bidirectional scanning. In this case, we are scanning in both directions and it goes almost twice as fast. Not completely twice because it's the turning point. The turning takes time. But at the beginning, you might need some realignment, but it anyway works very well. So you go faster. So this is a trick to go faster with a single point confocal.
To start with, we will acquire a reference image using standard, slow, galvanometric imaging, denoted Galvano in the software. This is slow but generates high quality images. For the single point confocal, we can choose to image in one direction, the unidirectional mode, or in both scan directions, the bidirectional mode. For this reference image, we will use unidirectional mode. The advantage of this is that for this microscope, it is easier to do good quality imaging in unidirectional mode. In this mode, we can also choose between a lot of different dwell times. The dwell time is the time the laser spends on a pixel. The longer dwell time, the more photons you collect, but you will also bleach more and you will increase the time to acquire an image. In this case, we'll choose a dwell time of 2.4 microseconds. The image size in Galvano mode is between 64 and 4096, depending on other settings such as dwell time. We will use an image size of 1024. That means 1024 pixels both in X and Y. The resulting time to acquire one image, the frame time, is 4.2 seconds. We are quite free to set the pixel size in the unidirectional mode. In this case, we use a pixel size of 0.56 micrometers to later be able to compare to multi-point confocal images. Let's go ahead and acquire a 1024 image in the Galvano mode. It took 4.2 seconds to acquire the image in Galvano mode. If the microscope is switched to the resonant mode, the image acquisition should be much faster. In the resonant mode, the frame time is now 130 milliseconds. The pixel size changed automatically to 0.26 micrometers when we switch from the Galvo to the resonant mode. So let's set it to 0.56 micrometers again. After entering the value, the pixel size automatically changes to 0.51 micrometers because the resonant mode is not as flexible as the Galvano mode. In addition, the option to choose dwell time is gone as the mirror is set to scan at its fastest speed. The microscope is currently in the unidirectional mode with the frame time of 130.3 milliseconds. We will change that to the bidirectional mode. This gives us a frame time of 65.6 milliseconds. We can compare the resonant image with the Galvano image. The image on the left is the Galvano image that was acquired earlier, and the right image is the image acquired in the bidirectional resonant mode. Both images have the same number of pixels, but the resonant image on the right has slightly smaller pixel size, resulting in a smaller image. The resonant image has less contrast and a smaller signal-to-noise ratio due to the shorter exposure time following from the fast frame rate. We'll now go ahead in bidirectional resonant mode and acquire a fast time-lapse where we will have no delay between the images but acquire continuously. We will acquire 50 images with a scan size of 1024 pixels, resulting in an image of 1024 times 1024 pixels. The total acquisition time was 3.2 seconds for 50 images. We will now acquire a time-lapse with a scan size of 512 pixels. This we will later use as a comparison between single-point scanning and multi-point scanning. Please notice that after decreasing the scan size, the frame time has decreased to 33.3 milliseconds. This happens as we are only scanning 512 lines now compared to 1024 lines previously. Let's start the time-lapse. The total acquisition time was 1.6 seconds for 50 images using a scan size of 512 pixels. We can see that there is noise in the image, but from one image we do not know how much signal and noise there is in one pixel. However, as we have acquired multiple images, we can compare one and the same pixel in different frames and calculate the signal-to-noise ratio in this pixel. This is of course best done by a computer, but if we make a movie of the frames, we can get the sense of the signal-to-noise ratio. We see that the image is not fixed but varying between different frames. This is because of the noise in each single pixel. The more variation we have, the worse the signal-to-noise ratio is. When acquiring with a fast frame rate, we collect few photons and we will in general have a low signal-to-noise ratio. Now we will continue with multi-point scanning confocal. We will start with a very brief refresher of the technology. At the bottom you see the laser light source. The green light from the laser is going upwards, straight through the dichroic mirror, and then through the spinning disk before it excites the sample. The emitted red light then goes back through the pinholes of the spinning disk before it is diverted to the camera sensor by the dichroic mirror. The imaging is confocal due to the pinholes in the spinning disk, and it is fast because we have multiple pinholes scanning the image paired with a camera sensor with multiple pixels. If we have a look at the basic animation of the spinning disk, starting with a still image of a disk that is not rotating, you can see a spiral pattern of the pinholes letting through light from a source behind the disk. Let's spin the disk to see the image. As the pinholes are moving, we can see an image of a half moon. As the camera is exposing when the disk is turning, we will thus not see the spiral pattern of the pinholes, but the resulting scanned image. In reality, the camera sensor is only covering a small part of the disk, and this is also the only area illuminated by the optics of the microscope. Let's have a look at the camera sensor image of a still disk. We can see the thousands of pinholes. We will now acquire some fast time lapses using the spinning disk multipoint confocal. We will start with setting up the imaging parameters for the camera. The first one is the binning of the camera. We will not use any binning. The second parameter is the bit depth. We can use 12 or 16 bits, where 16 bits give us higher dynamic range, but for this camera it is slower to acquire 16 bits than 12 bits, so we'll use 12 bits for high speed. The third parameter we need to set is the gain. We have three choices: full, balanced, and sensitivity. Sensitivity gives us the highest gain, so we'll use this as we expect short exposures to give a small number of acquired photons. We then proceed to set the exposure time. In the list you will see some of the available exposure times we can use. There is also an entry called 1 frame with an unspecified exposure time. We only know that it's between 10 and 20 milliseconds long. This setting gives us the highest available frame rate for continuous acquisition. We can choose even shorter exposure times, but the continuous acquisition will not be faster because the camera hardware needs some time to handle the image data. Thus, if we would choose 1 millisecond, the camera would expose for 1 millisecond, but it would not be ready to acquire the next image for more than 10 milliseconds later. With the 1 frame setting, the camera will optimize the exposure time for one image so that it acquires light all the time until the camera is ready to acquire the next image. The camera sensor has 1608 pixels times 1608 pixels, and for the first acquisition we will use the full sensor. If we had used the region of interest to define a smaller area of the sensor, it would lead to higher frame rates. We will test this later. The microscope is in the confocal mode, and the pinhole size of the spinning disk we are using is 50 micrometers. Now we will acquire a fast time-lapse of 50 images in the same manner as we did for the resonance scanner. The acquisition time for 50 images was 814 milliseconds, resulting in a frame time of 16.3 milliseconds. Please note that the pixel size using the 20x objective is 0.56 micrometers, and for one and the same objective we can only change this by binning. For later comparison, we will now acquire stacks using a region of interest. From the drop-down list we will choose the 512 by 512. We will also need to reset the 1 frame, as the limited ROI will take less time to image compared to the full frame. You can see that the 1 frame acquisition time is now between 5 and 6 milliseconds. This is because of the smaller amount of pixels in our region of interest. We will now go on and acquire 50 consecutive images as fast as possible for our region of interest. The total acquisition time is 262 milliseconds, resulting in a frame time of 5.3 milliseconds for our region of interest. Compared to the frame time of 16.2 milliseconds for the full frame, our region of interest only takes 1/3 of the time to image. But when we only expose for 1/3 of the time, our signal-to-noise ratio should be worse as our signal is smaller because we collect less photons. Let's do a comparison of the images. On the left you see the full frame image, and on the right the image based on the region of interest. The scale is the same, but the number of pixels in the full frame image on the left is almost 10 times as many as in the right image. To compare the image quality, we need to zoom in. We can see that the right-hand image is a bit more grainy than the left, showing that the signal-to-noise ratio is lesser than in the left image. This can be seen in even more detail if we zoom in on a structure. When we used the region of interest, we gained acquisition speed, but we lost quality because we collected less light. To counteract the loss of quality, we could try and increase the power of our excitation light. As long as we do not saturate the fluorophores, we would increase the emission of them by increasing the excitation light power. We will test and increase the laser power from 15 to 45%. We will now acquire 50 images using the same region of interest. The only change we've done to the imaging settings is to increase the laser intensity to 45%. The frame time for an image is the same 5.3 milliseconds as for our previous region of interest image acquisition. But using 3 times the laser power, 45% instead of 15%, has reduced the graininess of the image. To see that, we need to compare the images we have acquired. To the left, we have our full frame image. In the center, our first RI acquisition, and to the right, the RI acquisition with 3 times the laser power of the other images. You can see that the right-hand image is of better quality than the center image, and almost as good as the left-hand image. If we zoom in on the structure, this becomes even more obvious. Qualitatively, we can see that the signal-to-noise ratio decreased when we decreased the exposure time, but we could increase it by increasing the emission using a higher laser power. We will now acquire a set of images with high laser power and longer exposure time. For this set, we'll keep our last setting of 45% laser power, but we will increase the exposure time to 30 milliseconds. In our earlier acquisition of the single-point confocal resonant images, we had a total frame time of around 33 milliseconds, so acquiring multi-point confocal images with 30 milliseconds exposure time gives us a possibility to make a comparison of the image quality we can receive if we use the same exposure time. We will do this comparison in a bit. First, we will make a quantitative comparison of our results for the multi-point scanning confocal. We can already see that the high laser power and long exposure time gave us an image of good quality. Let's compare this to our other spinning disk images. The images are arranged with the original full field of view image in the upper left corner. Then in the upper right corner we have the RI image using the same laser intensity as the full field of view, but with a shorter exposure time because the camera is faster acquiring the smaller image. In the bottom left image we have the same RI, but the laser power was increased 3 times. In the bottom right corner we have our last RI image with a long exposure time of 30 milliseconds and with the same high laser intensity as in the previous RI. Here we have applied a mask to the same structure in the different images. The mask can be seen as the red area that covers the cell walls. The black background is not included in the mask. We can calculate the average signal-to-noise ratio of all the pixels in the mask to make a quantitative comparison of the different time lapses. The signal-to-noise ratio of our image with a 16.3 milliseconds exposure time is 15.6. When we decrease the exposure time to 5.2 milliseconds, the signal-to-noise ratio decreases to 8.9. Actually, the ratio between the signal-to-noise ratios is quite close to what you would expect when you have one exposure time that is roughly 3 times longer than the other. In the next image, we have an exposure time of 5.2 milliseconds, but we have 3 times the laser intensity compared to the previous images, and we get a signal-to-noise ratio of 12.5. In the last image, we have exposed for 30 milliseconds using the high laser intensity, and our signal-to-noise ratio is 28.9 due to the long exposure time and the strong excitation of the fluorophores, both working in concert to increase the number of photons we collect.
So here are the conclusions for this speed versus noise workshop. The options that we have to increase the speed of imaging for if we image only one color. First, on the camera-based system, they are much faster than single-point confocals, so they are a good option to go faster. If we want to increase the speed of imaging on any type of system, we can always reduce the number of pixels. We can also use a lower bit depth. On single-point confocals, the options that we have to go faster are to use a resonance scanner, or to image in bidirectional mode, or to use larger pixels, so we have less pixels in the same scan area. Unfortunately, that lowers the resolution. On camera-based systems, to go faster, we can increase the readout rate. We can also use larger pixels by binning, and again, this leads to lower resolution. The main drawback with imaging fast is that the images become noisy. To visualize the noise in a single image, one looks if there is high contrast, and because the contrast goes down when the images become noisy, we can also see sometimes that the image becomes grainy. But it's a little bit difficult to estimate the noise with single images. It is much easier to see the noise when taking 3 consecutive images at fast speed, one after the next. And then when I play through the 3 images, the random changes that happen between the images are the noise. The main source of noise is shot noise, which is due to the statistical nature of light. To improve the signal-to-noise ratio, one must increase the number of photons that reach the sensor. So how to do that? We can increase the illumination power. We can also integrate photons for a longer time. So for example, use a longer exposure time for a camera-based system. We can also use longer pixel dwell time, also called slower scan speed, on single-point confocals. Both strategies are equivalent to improve the signal-to-noise ratio, as we saw in the video. Unfortunately, when we illuminate for a long time, we also have a higher risk of sending the fluorophores to the dark state, and this causes apparent bleaching. So if we look at the 3 modalities that we have compared here, a spinning disc confocal, single-point confocal with a resonance scanner, and single-point confocal with a galvanometric scanner, we can see that the spinning disc confocal is by far the fastest. The single-point confocal with a resonance scanner was next, but anyway much slower. And then much slower is the galvanometric scanner. So the spinning disc confocal is fastest, and we have low noise in the images, and also low bleaching. But unfortunately, the pinhole size is designed for only one objective, which on our case is a 100x 1.4 objective. And therefore, we have a lower sectioning power with the 20x 0.75 that we were using in the video. The resonance scanner is the second fastest system, but it produces noisy images. And then the galvanometric scanner is by far the slowest, but with low noise in the images and the flexibility to adjust the pinhole for each objective. So now I would like to mention something that can rescue the resonance scanner, is the power of artificial intelligence to denoise noisy images. And this is not specific to resonance scanner. So any noisy images can be denoised with artificial intelligence. And this is what it looks like. So you can see on the left side the original image acquired with the resonance scanner at 33 milliseconds. And after denoising on the right side, it's quite easy to see that all the grain has gone and all the details came back. And from the signal-to-noise ratio, you can appreciate that we go from 3.2 to 13.4, so the signal-to-noise ratio is much higher in the denoised image. One can take AI denoising with a pinch of salt because it makes errors as well. And how to visualize the errors? We use the same technique as we used to look at noise. So we can take 3 images in a consecutive manner very quickly, one after another, and then denoise the 3 of them. So if we have normally nothing should change in the sample, if we image the 3 images very quickly, or if the sample is fixed. So this is an example of 3 consecutive images of a fixed cell labeled with tubulin. And so we have a variation in the denoise images, of course, also in the noisy image, but in the denoise images, you can see at the bottom row that even though it's hardly visible in the original image that we have fibers, the tubulin fibers, AI finds the fibers, but in each of these images, it finds different fibers. So some of them are always there, but many of them are different between the three images, and that clearly shows the limitation of using AI to denoise images.